Look, I'm absolutely pumped about our topic today because we're diving into a totally hidden world. We're exploring the wild realm of nanotechnology, specifically how we actually analyze materials at the incredibly small nanoscale. When you're literally building materials atom by atom, you absolutely need specialized tools to figure out what you've just created, right? So today, we're unpacking the ultimate tool for that exact job. It's basically our nanoscale detective.
And it all starts with a pretty massive puzzle. How on earth do we identify chemicals on particles we can't even see? Imagine trying to investigate the surface chemistry of something 1,000 times thinner than a human hair. You definitely can't just throw it under a normal microscope and expect to see what chemical bonds are hanging out there. We need a way to essentially walk up to this tiny nanoparticle, ask it, hey, what are you wearing on your surface today, and actually get an answer in a language we can understand.
Well, that translation, that comes from our star detective, FTIR, or Fourier Transform Infrared Spectroscopy. At its core, this is a brilliant technique that measures exactly how a sample absorbs infrared radiation. By looking at that absorption, we can perfectly identify specific chemical bonds and functional groups. It's kind of like shining a very specific, invisible flashlight onto our microscopic sample and measuring exactly which wavelengths of that light get soaked up. And because every single type of chemical bond absorbs its own specific wavelength of infrared light, we get this flawless chemical blueprint.
Okay, so here's our game plan for today. 1. Inside the FTIR machine. 2. Reading chemical fingerprints. 3. 4-core nanotech rolls. And 4. The future of nanomaterials. Let's jump right in.
Part 1. Inside the FTIR machine.
Let's actually trace the journey of a photon through this crazy gadget. It kicks off at the IR source, which fires a beam of infrared light. That light shoots straight into the interferometer. Now, what's super cool here is that this interferometer uses both a fixed mirror and a moving mirror. So that moving mirror actually creates this complex interference pattern with the light before it even gets close to our sample. Next, that highly manipulated beam hits our nanoparticle sample. Some of that light gets absorbed by the chemical bonds, and whatever doesn't get absorbed passes right through to the detector. Finally, all that raw data gets zapped over to a computer, which runs a heavy-duty math equation, the Fourier Transform, to flip it into a graph we can actually read.
Which brings us to Part 2. Reading chemical fingerprints.
So, a standard FTIR graph plots transmittance percentage on the vertical axis against wavenumber on the horizontal axis. Notice those really sharp, plunging dips on the line? Since the vertical axis measures the light that transmits through the sample, a dip means that specific wavelength of light got absorbed by the nanoparticle. Think of this whole spectrum like a visual barcode. Every single dip you see corresponds to a specific molecular vibration, like a chemical bond physically stretching or bending.
And here is exactly how we crack that barcode. We just cross-reference where those dips happen, the wave numbers, to known functional groups. For instance, if you spot a big, broad dip between 3200 and 3600, boom, you've got an OH stretch. That's a hydroxyl group. Dip between 1650 and 1750, you're looking at a CCO stretch, so a carboxyl group. It completely takes the guesswork out of it. By just matching your graph's numbers to a standard table, you map out the entire invisible chemical landscape of your nanoparticle.
All right, Part 3. 4-core nanotech rolls.
Our nanoscale detective basically works 4 major jobs. It handles surface chemistry analysis, green synthesis verification, confirmation of functionalization, and interaction and bonding insights. Let's break down the micronarrative for each of these real quick. First up is the absolute baseline, surface chemistry analysis. Look, before you can modify a nanoparticle, you have to know exactly what you're starting with, right? FTIR sweeps the particle's surface and identifies whatever functional groups are already there. It's basically a chemical inventory system. It tells researchers right out of the gate if the surface is rocking hydroxyls, amines, or carboxyl groups.
Now for role 2, let's talk about green synthesis. Instead of relying on harsh, toxic chemicals to build nanoparticles, scientists are doing something amazing. They're combining simple plant extracts with metal salt solutions to create green synthesized nanoparticles. It is a massive, eco-friendly game-changer for materials science. But here's the catch. How do you actually prove your plant-based method worked? That's role 2, green synthesis verification. When you run your new green nanoparticles through the FTIR, the spectrum will literally highlight the specific plant biomolecules, stuff like natural polyphenols or flavonoids. Because these organic molecules act as natural reducing and capping agents, finding their unique fingerprints on the particle is your ultimate proof that the green synthesis was a total success.
Moving on to role 3, confirmation of functionalization. I always think of this as a nanoscale makeover. It's when you take a plain, bare nanoparticle and try to attach something powerful to it. Maybe a protective polymer, a life-saving drug, or a targeting ligand that hunts down specific cells. The problem is, you can't see the drug attaching, but FTIR, it provides the hard proof that the attachment actually happened.
And what's wild is how obvious the proof is when you compare the data. You run a spectrum on the bare nanoparticle, right? Then you run a second spectrum on your newly functionalized one. You layer them over each other and you look for entirely new peaks. If your bare particle had 0 carbon-nitrogen bonds, but your attached drug has them, well, if those brand new peaks pop up on the second spectrum, it definitively proves the functionalization worked. Makeover complete.
Finally, we have role 4, interaction insights. This goes a step further than just proving attachment. It's all about dynamic, real-time interactions. When nanomaterials meet biological targets or polymers, they bind together. And FTIR is actually sensitive enough to monitor the structural shifts or the changes in vibrational frequencies as that binding happens in real time.
The smoking gun here is all in the comparison. Actually, scratch what I said earlier about looking for new peaks. When we're looking at interactions, we're really looking for a shift in the existing peaks. We compare the before and after spectra and we look for a distinct movement. A physical interaction, like binding to a biological target, literally alters how those chemical bonds vibrate. That change in vibration makes the peak shift its position on the graph. It proves without a doubt that a physical, structural interaction went down.
Part 4. The future of nanomaterials.
So why is FTIR the absolute go-to tool for material scientists everywhere? It boils down to 3 massive advantages. First, it is insanely fast. You get your chemical fingerprint faster than you can brew a cup of coffee. Second, it's non-destructive. You shine some light on your precious sample, you get your data, and you can still use those exact same nanoparticles for your actual experiments. And third, it's just incredibly reliable, backed by decades of proven accuracy.
And because of those benefits, this technology is now absolutely vital for confirming synthesis in some of the most important fields out there. Think about advanced drug delivery, where nanoparticles carry targeted cancer treatments right to a tumor, or next-gen biosensors, energy catalysis, and just smart materials in general. Literally none of these life-changing advancements can confidently move forward without FTIR there to verify the surface chemistry every single step of the way.
We really do have a window into the invisible now. We have this amazing tool that translates the physical vibrations of molecular bonds into a clear visual language. It lets us build the future, molecule by molecule. So I'll leave you with this. Armed with this ultimate nanoscale detective tool, what breakthrough custom nanomaterial are we going to build and verify next? The possibilities are literally endless. Thanks so much for hanging out with me for this explainer, and keep exploring.